Hey everybody, this is Mr. Lowry here. Today we have for homework this worksheet, which is yellow, kind of looks a little kind of orangey in the video, but this is a yellow worksheet, special case quadratics and two-step factoring. So we've been talking about factoring a lot, and last week we had an in-class assignment where we multiplied a bunch of binomials to look at some patterns so we could factor. So today we kind of just built on that, and a lot of students are getting pretty good at factoring and could maybe even factor these four problems pretty quickly because these are similar to what you had on your last Thursday night's homework. But what I wanted to do today is just give you a couple little extra techniques and strategies to help you factor because we want to be able to actually do these pretty quickly as we go. All right. Another thing we talked about today is that some things are not factorable. When we have a number that's not factorable, for example, like 7, this is 7 times 1, we can't really break it down other than factors of itself and 1. We call that a prime number. And we also sometimes have prime polynomials as well. So a number like 8 is not prime because we can break it down into two numbers that aren't 8 and 1. All right, but 7 we can't do that. So this is called a prime number. It can't really be divided further unless we're talking about dividing it by 7 or 1. And 8 is called a composite number, which is not important for this assignment, but that's what it's called. So in our first 4 here, we're factoring these quadratic trinomials. Quadratic means degree 2, or in other words, they all have a squared term. Trinomial means there are 3 terms, so you can see that they're all 3 terms. And I'm going to show you some techniques. Okay, so this method here that I'm going to show you first is called the X method, okay, or the cross method. And it's not really any different than we did last week on Thursday. It's just a way of organizing your information. Okay, from last week in class assignment, we just multiplied a bunch of binomials, and when we did that, we ended up with these quadratic trinomials. So just from experience, just from the practice that we did on Thursday, we can predict that this quadratic trinomial is the product of 2 linear binomials. So we're looking for something like this, where we have like an m up front, and we have these 2 binomials, and then we're probably going to have like a minus and a plus, and we got to figure out what these numbers are right here. I'm going to put question mark, question mark. Okay, you don't have to write that, but that just kind of showing you what we're doing. We're trying to figure out what these 2 numbers are. That when I multiply these 2 polynomials, I get back to here. So we're kind of trying to unmultiply or undistribute here. Oh, there's the Jeopardy bell. Do, 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 do. Okay. So how do I know it's a minus and a plus? Well, this last number right here, -7, it has to be a product of whatever numbers are in these binomials, whatever these mystery numbers are. And when I multiply a negative by a positive, I get a negative number. So the fact that this is negative right here tells me that these cannot have the same sign. It's got to be minus plus or plus minus, and since the order doesn't really matter, I just wrote minus plus. So in this cross method, what I do is I put the constant term, which is this guy that doesn't have a variable, in the top, and then I put the linear term, the linear coefficient, in the bottom. And what I'm doing is I'm just going to test out some numbers. So I'm going to switch to pencil right now so I can erase. I'm testing out 2 numbers that go here. And this cross method is just a very quick way of checking to make sure I have the right numbers. We know, we just talked about a minute ago and last Thursday, that these 2 numbers have to multiply to -7. But not only do they have to multiply to -7, when we add them together or when we combine them, they have to give me a -6. Those are all based on patterns that we saw last week, so if you're not sure why that's the case, I might go back and look at your in-class assignment from Thursday or your homework from Thursday, because we talked about those there. You can go back to the video posted for those assignments as well. All right, so we're just going to test some stuff out, right? Well, there's actually only a few numbers that multiply to 7. It's like a -7 or a 7 and a 1, so I'm going to try 7 and -1. Okay, let me erase those circles really quick. So I'm just using this box as a tester area. So 7 times -1 is -7. That's what I want. So these 2 numbers will multiply to the top area, and when I add them, I should get the bottom area. So 7 plus negative 1 is actually not negative 6, it's positive 6. So I know those aren't the two numbers that I'm looking for. So let me go back here, and let's try, instead of positive 7, negative 1, let's try negative 7, positive 1. Okay, so if I multiply negative 7 and positive 1, I get the negative 7 that I'm after. If I add them together, I get negative 6, which works. So these are the two magic numbers that I want that will fill in the gaps of these two binomials right here. So what I have is I have a m minus 7, and I have a m plus 1. And that is my factored form. So this all comes from patterns and comes from experience. It comes from multiplying polynomials a bunch of times and finding those patterns, which is why we did that activity on Thursday. All right, let's take a look at another one here. So again, my prediction here, and this is just based on experience, is that we're going to have an r and an r. We have two binomials. We know that the numbers in here are going to have to multiply to 21, but they're going to have to add to 3. I also know that the signs here have to match. Over here, we knew we had a negative and a positive because that last constant term was negative, and we only get that by multiplying negative and positive. Over here, the back number is not negative, like this one, it's actually positive. And that tells me either these are both positive, both plus signs in these binomials, or they could also both be negative signs. But when I combine them, I have to end up with a positive number, and there's no way to combine two negative numbers to get a positive in the middle. So I know that these have to be plus signs. All right, now the question is, what numbers are they? Well, I have a 21 up top, and I have a 3 on the bottom. So I'm taking this and putting it here, and this and putting it here. And we're just going to test some stuff out. We're looking for factors of 21 that will add to 3. So some factors of 21 are 7 and 3, right? 7 times 3 is 21, check. But 7 plus 3 is 10, not 3. And so those are not my magic numbers that are going to work, okay? The only other factors of 21 that we can work with are 21 and 1. So 21 times 1 is 21, that's good. If I multiply, if I combine those, I get a 22 though, and that's not what I want. But now we've actually exhausted all of our possibilities. There's no other options here. So if you list out all the factor pairs that give you 21, you can do 1 times 21, you can do 3 times 7, and those are pretty much the only pairs that give you 21. So I already tried these guys and they didn't work, and I tried these guys and they didn't work, and there's no other options, which means that this polynomial is not factorable, like 7. Or, in other words, you can only divide this polynomial by itself and 1. So this polynomial we call prime, which essentially means we can't factor it down any further. So sometimes you'll see that. Okay, let's take a look at number 3. So again, I'm going to set up kind of what my final answer looks like, or what I expect it to look like. Again, this is just from experience. So if you're wondering, like, how does he know it looks like that? Well, it just comes from multiplying stuff like this over and over and over to see, like, oh yeah, when I multiply stuff like this, it turns out to be quadratic trinomials. So it's all about, we've talked about inductive reasoning in class. The reason why I know that this is going to factor to 2 linear binomials is inductive reasoning. All right, now let's set up our signs. This number is positive, right? Positive 12, which means these numbers have to match. The only way I get a positive number is a positive times a positive, or a negative times a negative. If I have a positive here and a negative here, that's going to give me a negative number, which I don't have. Or if I have a negative and a positive, that also gives me a negative number. So I know that these have to match. I also know that they have to be negative, because the only way I can get a negative number by combining, and see, that's going to be the negative number. I have to combine these to get a negative. If I multiply them, they give me a positive. If I combine them, they give me a negative. The only possibility is they're both negative. So now we're going to set up our little cross guy here. We'll put a 12 on the top and a negative 2 in the bottom. And I mean, we know this from last week, but we're just looking for factors of 12. These numbers that we're looking for have to multiply to 12, and they have to combine to give me a negative 2, and we know they're both negative. Okay, so let's try some stuff. Let's try a negative 1 and negative 12. Okay, if I multiply those, I get Positive 12, check. If I combine them, I get a negative 13. That's not what I want, so it's not those guys. Whoops, I used pen. Uh-oh, can I erase? That's all right. Let's try some other factors. What about negative 2 and 12? Sorry, that's not going to work. Negative 2 and negative 6, excuse me. Okay, if I multiply negative 2 times negative 6, I do get the positive 12 that I'm after. If I combine them, I'm going to get a negative 8, so that doesn't work either. Okay, so it's not the 2 and the 6. Okay, what about 3 and 4? Okay, so if I do negative 3 and negative 4, I multiply those and I get 12, check. If I combine them, I get negative 7, and I think I've just ran out of options. So I'm going to list the factors of 12 just to double check that I've checked them all. I did the 1 and the 12, that didn't work. I did the 2 and the 6, that didn't work. I did the 3 and the 4, that didn't work. So notice I'm just going in order. The next one up will be 4. Like I'd say it's 4 times 3, but I already have this 3 and 4 pair. So I'm just listing out all the different factor pairs that will give me 12, so I can systematically say it wasn't that set, and it wasn't that set, and it wasn't that set. So if all my options are exhausted, then again this is going to be prime. Or not factorable. I think in the answer key it might say not factorable, but we know that prime and not factorable are essentially the same thing. Okay, we got one more. So again, I'm going to set up what my final answer is going to look like. It should look like two linear binomials if this works. Since this is negative, I know that these don't match. I have a positive and a negative. So it's going to look something like that if we can find a pair that works. Let's set up our cross. I'll put my constant term in the top. I'll put my linear coefficient in the bottom. So that's the last number and the middle number. So let's look for some factors of 18. So we got 1 and 18, we got 2 and 9, we got 3 and 6. As you do this more and more often, you might get kind of better at this, but let's just try a couple just for, practice. So let's say we're testing the 3 and the 6. Let's try the 3 and the 6. We know one of them has to be negative, so let's try that. Positive 3 times negative 6 is negative 18. That's exactly what we want. 3 plus negative 6 is negative 3. That's not what we want, so it's not that guy. All right, well, let's try the 9 and the 2. Let's do a negative 2 and a positive 9. Okay, 9 times negative 2 is negative 18. That's what we want. Negative 2 plus 9 is positive 7, and I want a negative 7, so I'm definitely close, but it looks like I'm going to have a negative 9 and a positive 2. Okay, so now when I combine those, I get my negative 7. So notice if this term in the middle is negative, I already know that these two terms are, these are opposite signs, but when I combine them, the result has to be negative, which means the magnitude or the size of the negative has to be greater. So I have a minus 9 and a positive 2. Okay, so two of these factored. 2 of these were prime. I kind of went through and tested some possibilities out here, so I know that some of you guys can do that faster, and that's okay, but I wanted to give you some strategies that are going to help you in the future if you don't see the factors right away. Just ways to test it, ways to organize your information, ways to do this systematically and quickly check so that you can have if you get stuck, you have a method to go use. Okay. Now this one is asking why I can't factor x plus 49, or x squared plus 49. If you look down here, this is actually kind of trying to get us ready for all of these. These are all what we call difference of squares binomials. In other words, we have a difference, which means subtract, right? Subtract, 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 subtract. And then we have a square. So I got n squared, and this is 11 squared. I got x squared, and this is 9 squared. I got 9 squared and n squared, and I got 4 squared. So we'll come back and do those in a minute. All of these are called difference of squares binomials. But what I wanted to point out is that this x squared plus 49 is actually not factorable. Okay, I'm going to show you why, then you can kind of use your own words to fill in the blank here. So this is not a written explanation. I'm not going to give you one. You're going to do the writing part, but I will show you what's happening. Okay, so if you think about just the three options that we have, right? You might be like, okay, well, where is this going to come from? Let's just make some guesses. Let's try x plus 9 times x plus 9. Oh, excuse me, sorry, not 9, 7. X plus 7, x plus 7. So you might notice that 49 is 7 squared, right? So what if we tried this, right? X plus 7, x plus 7. Well, what that's going to give us is x squared plus 7x plus 7x plus 49, because when we FOIL, F is for F-O-I-L. F is for first, right? So x times x, x squared. O is for outside, 7 times x, that's 7x. I is for inside, 7x. And then L is for last, 7 times 7, it's 49. So altogether, I got x squared plus 14x plus 49 when I combine my like terms. So obviously this is not how this factors. This does not factor to this because when we FOILed it, we get something different. Okay, so that's not going to work. Okay, well let's try both minuses. Maybe that will result in some canceling happening, right? All right, so again with the FOIL, I got x squared up front. I got a negative 7 for my outside terms. Sorry, negative 7x. I got a negative 7x for my inside terms. I get a positive 49 for my last terms. These combine again. I get x squared minus 14x plus 49. And that's not what I was looking for either. So this does not factor to this, because when we multiply these, we get something different than that. So that's not going to work. Okay, so let's try x plus 7, x minus 7. Okay, so FOIL, x times x is x squared. Okay, outside terms, I get a negative 7x. Inside terms, I get a 7x. And then last terms, I get a negative 49. So altogether, that's x squared minus 14x minus 49. Oh, sorry. No. These cancel, excuse me. X squared minus 49. These actually cancel. Which is close, but not exactly what I was after. So basically, like, none of these options work, and there's no other options. There's no other, like, ways to check. So this is the deal. When you are when you are multiplying two binomials, the only way you're going to get the middle linear term to cancel is to have a plus and a minus of the same number. Okay? So like up here, if you notice, most of the time when we multiply two binomials, we get a quadratic trinomial. So linear, sorry, I might have said that wrong. Let me try that again. Most of the time when you multiply two linear binomials, like here and here, the result is a quadratic trinomial, right? And we saw that here as well. We multiply these two linear binomials, we get a quadratic trinomial. Multiply these two linear binomials, we get a quadratic trinomial. The only situation that doesn't happen in is this situation. We call this a conjugate pair. Basically the same exact binomials, except one's plus and one's minus. We've got those opposite signs. So the only way we're going to get those middle terms canceling is if these signs don't match each other. But if these signs don't match each other, then the last term has to be negative, because when we multiply a positive by a negative, the result is negative. So the reason why we can't factor, this is what we would call a sum of squares, right? Sum is plus instead of minus. We can't really do that because there's the only way we get the linear term to cancel out when we're multiplying binomials is to have them be opposite signs, and if they're opposite signs, that results in a negative number. So that's kind of what you need to write about. You can show some examples here, but again, I'll kind of say that again, and maybe you can put it in your own words. The only way we get a binomial from foiling is when these two guys are conjugate pairs, and otherwise we have opposite signs and the same number. It's the only way we get a binomial. But if these are opposite signs, then the last term is always going to be negative. It will never come out positive. If these signs don't match, which is what we need for the middle terms to cancel, then I can't get a plus out of that. It's always going to be a minus. Okay, so that's kind of your description there. All right, now these are all what we call differences of squares. So you'll notice there's minuses all over the place. All minuses, no pluses, all minuses. All right. Now, from our experiences that we were working on last week, we know that these come from conjugate pairs. So we talked about these terms in class today. This is a difference of squares because I have a difference. That's minus, right? Difference means minus. And this guy right here is x squared, and this guy right here is 9 squared. So when you look at 81, you're like, oh, that's a perfect square. That's 9 squared. So it's the difference of two perfect squares, of two things that are getting squared. In this case, an x, and in this case, a 9. And so what I do is I take x, and I take 9, and I put them together in a binomial, and I make sure I alternate the signs. So x plus 9, x minus 9. You probably remember that from last week. This right here is what we call a conjugate pair. Okay, you don't have to write that for your answer. The answer is this. Okay, but again, it's part of learning how to factor is to predict what you're going to have happen. The only way we get a binomial, a quadratic binomial, without the linear term is when we multiply a conjugate pair. Two linear binomials that are conjugate pairs. Okay, so that's just some language for you. All right, so notice what happened here is really I need to figure out, what the square root of 81 is. If I can figure out what the square root of 81 is, it's like, oh, that's 9. Okay, that's the number I need to plus and minus. Okay, so the same thing is going to be true here. Notice this is a difference of squares binomial, right? So I know that these two terms have to be the same number, but they have to be opposite signs. That's the only way the middle term, the linear term, will cancel out like we had going on up here. So the question is, what is the square root of 121? Now don't try to take the minus sign. Don't square root that if you're using a calculator, because that's going to give you an error, because if you take the square root of a negative number, it's like imaginary. So don't worry about the negative. We know that this has to be a plus and minus, so don't worry about that. The square root of 121 is 11. And there we go. That's how you factor a difference of squares binomial. It's actually pretty fast. Okay, now those two, 6 and 7, are very similar to what we saw in last week's homework. Those are kind of the basics, right? Now, as we get more advanced, we have numbers up front, and that's okay. We can still do the same thing. So notice how we were really trying to figure out, well, what squared is 121 and what squared is 81. And so it's kind of like we took the square root of these numbers to figure out the number that we needed. Right, square root of 121 is equal to 11. And we're like, oh, okay, 11 goes in there. Or square root of 81 is 9. Okay, 9 is the number that goes in there. We're going to do the same thing over here, but we're just going to do it twice. So we still know we need a conjugate pair because this is a difference of squares. We just got to figure out what squared is 81n squared. So we're just going to take the square root of it. The square root of 81 is 9. The square root of n squared is n. And so this is the first puzzle piece that I need to use a 9n. That's one of the building blocks of my conjugate pairs. Okay. The other one I need to do, take the square root of 16. That's going to give me a 4. All right, so I have a plus 4 and a minus 4. Okay, now notice these have to be exactly the same except for the sign in the middle. If they're not, then the whole thing falls apart. Right? Notice here I have an n and an n, an x and an x, right? An x and an x here. Now this is a little different because I have a little bit more, but they still match, right? It's a 9n and a 9n. So if I were to FOIL this, just to check, sorry, let me be clear. This is the answer right here. But to double check to make sure that that was actually the case, I got a 9n and a 9n. I got a 4 and a negative 4, right? Let's see what happens. This is just a check. 9n times 9n is 81n squared, okay? When I do these two guys, I'm going to get negative 36n. And down here in the bottom left corner, I get a positive 36n. And then in the last bottom right corner, I get 4 times negative 4, which is negative 16. And since these are now basically additive inverses of negative 36 and a positive 36, both with an n, they're going to cancel, and I get, again, this difference of squares. Okay, so the only way you get a difference of squares quadratic is if the middle terms cancel, and that only happens when you have a conjugate pair. In other words, identical binomials except for the sign in the middle. All right, So let's do that faster this time because we can do it faster. I'm kind of dragging it out because I'm explaining why this is happening, but really in practical terms it's pretty fast. So notice that it's a binomial, right? There's a difference. This is something squared and this is something squared. Let's just figure out what those things are. So take the square root of 25v squared, that's 5v. Take the square root of 9, that's 3. So I got 5v plus 3, and I got 5v minus 3. If you wanted to FOIL that to check, you could do that, or use the box method, or however you want to multiply, you can do that, but that's how it's done. Okay, let's do 11. I'll save 10 for you. Now, again, if you're using this video to help you, that's great. You're welcome to practice, but we should try to be gaining some independence here. So before you watch me do the next one, try these on your own and see if you can, like, if you're getting the hang of it. Okay, and then we'll check in a second. Okay, so coming back from your break or your pause here, let's take a look at, actually let's do 10 because you don't have that one in the answer key. So I would just take the square root in both of these. This is a 5p, this is a 9. So 5p plus 9, 5p minus 9. That's it. Okay, over here, take the square root on both sides. We're going to get a 7p and a 9, so those are my two building blocks. 7p plus 9, 7p minus 9. Okay. All right, now the next section here, these next little bit here, is actually another special case. So one of the special cases that we just looked at was the these difference of squares. Because remember that most of the time when we multiply two linear binomials, we get a trinomial. But that's not always the case. So there's a couple special situations that we take into account, right? Difference of squares is one of them. Okay. Another one is when we square a binomial. Okay. So this is a very common mistake to make, and we talked about this in our warm-up today. This is actually not equal to this. People want to apply the power of a product property, but this is not a product. So you could do this if you had 9x in parentheses and you wanted to square it. You could say this is 9 squared x squared, or 81x squared. But notice that this is a single term, in other words, a monomial. There's no add or subtract. Excuse me, no add or subtract in there. This is not a monomial, it's a binomial. And so what we do here is when we have a binomial squared, we don't try to use that property because that doesn't apply here. What we do is we expand, right? That 2 means 2 copies of x minus 9, and then we FOIL. Okay, so when we FOIL, we get x squared for our first term, negative 9x for our outside term, negative 9x for our inside term, and then we get a positive 81 for our last term, negative 9 times 9. So notice what's going to happen here is this negative 9 is actually going to get doubled when I combine like terms. Oh, sorry, let me rewrite that. I should be doing this in pen. All right, so that's like my final answer here. And again, it all comes down to expansion, right? If you were to just expand this, you'll see that it doesn't equal that. Here, though, you can expand and show that these are the same. That 2 means 2 copies of 9x, but notice the difference here is here I have 2 terms separated by subtractions, and here I just have like a monomial and a monomial, and this is all ends up being multiplication. So I get like 9 times 9 times x if I rearrange the factors there, which gives me 81x squared. So this whole thing up here, this is all what's called power of a product. It's a property of exponents. It only works when you have a power of a product, or in other words, a monomial, things getting multiplied. Okay, this is a different situation. Now, what I hope that you can see from that is that negative 9, 2 things happened to it. It got squared to give me the 81. That makes sense. But it also got doubled to give me that negative 18, right? Negative 9x and negative 9x when I combine gives me a negative 18 because there was two of them from the O and from the I. Okay, so this is what we call a perfect square trinomial. It's a special kind of trinomial. It's a trinomial that we get when we multiply the same binomial against itself. So here's what's going on. This is 9 squared, and this is 9, well, sorry, let me go back. This is negative 9 squared, and this is negative 9 times 2. So that negative 9 got doubled for the middle term, and it got multiplied for the last term. So in these ones here, these are all actually perfect square trinomials. So let me show you that idea. This right here is 4 squared, right? This right here is 4 times 2. And when you recognize that, you're like, oh, okay, when I see that pattern of like it's doubling 4 and it's squaring 4, then I know that that came from what we call a squared binomial, right? So this is my answer. But if you wanted to, you could still use the cross method. So let's try that. So I need factors of 16 that add to 8, right? The two magic numbers that I'm looking for, I got a v and a v. Looking for two numbers that when I multiply them, they give me a 16, and when I add them, they get 8. Well, let's check out our options. So I could do like a 1 and a 16. Those multiply to 16. But when I add those together, I get 17, which is not what I want. Okay, what if we tried 8 and 2? Okay, when I multiply those, I get a 16. Awesome. But when I add them together, I get a 10, and that's not what I want. So let's keep going down the line. What about 4 and 4? Okay, those multiply to 16, but when I add them together, I get 8. Okay, that's actually the ones that I want. So I want v plus 4, which is the same thing as this guy, right? So you're noticing, oh yeah, okay, they're both 4s, but they're not opposite signs like we saw on the previous page. They're actually the same sign. And we can rewrite this as this right here, right? This is just some binomial times itself, which we can write as this guy. Okay, so all 4 of these here follow that same pattern. They're perfect square trinomials. Okay, so actually I think I goofed. This is the one we have up here, which I guess that's fine. That's okay. Right, notice this is 9 squared, and this is, well, actually it's negative 9 squared. The reason why I'm writing it like that is because this is negative. This is negative 9 times 2. Okay, so I'm seeing that same pattern, right? That's not true for every trinomial. If you go back over here, like, you can't take the square root of 7, right? And even if you could, like, if you took the square root of 7 and doubled it, it wouldn't give you 6. So we can still factor these, but these ones have a special pattern. We can factor them like normal if we wanted to, but if we can like see more patterns, if we can start spotting patterns, we can factor faster. So we're like, oh, I'm taking that negative 9 and I'm squaring it to get this and I'm doubling it to get this. That must mean that I have 2 factors that both have a negative 9 in it. Okay, so I can write it like this. You could also write it like this. Either way, it's the same idea, but this is a little bit shorter. Okay, let's take a look at this one. This one is 7 squared, right? 49 is 7 squared, and lo and behold, this is 7 times 2. Okay, so I doubled 7 to get 14, and I squared 7 to get 49. That must mean I have 2 factors that both have a plus 7 in it. Okay? Here I got a negative number, and here I got a positive, like perfect square. So I'm thinking this is negative 10 squared. It's also 10 squared, but since this guy's negative, I need that, that negative. This is negative 10 times 2. So, okay, negative 10. It doubles to get the middle guy. It squares to get the last guy. All right, so that means I have 2 factors with a negative 10 and an r. I'll just write it like this, and we're good. So patterns are great. Inductive reasoning is going to help you factor. Recognizing, how stuff like this works and doing it, a few different times and explaining it is going to help you recognize those patterns later that were actually going to make your factoring life a lot easier. Okay, so I'm trying to point out the patterns that are going to help you out a lot. They're going to be shortcuts for you. When you get into SM3, you're going to have to factor like quick. You're going to have it dialed in. Okay, now last week we also talked about something called the GCF, right? The greatest common factor. We talked about like undistributing the greatest common factor. And sometimes after you do that, there's still more work to be done. So we're going to just practice taking out the greatest common factor, which is a review. But after we do that first step, there's going to be a second step, which is why I call these problems back here two-step factoring. So we did our special cases. What were our special cases? Our special case quadratics were our difference of squares, binomials, right? Those are special cases. And our perfect square trinomials. Those are also special cases. All right, here is our two-step factoring ideas. Okay, so let's start by looking at all the terms, in this case 2, and seeing if there's a greatest common factor. In other words, what goes into both of those? Well, 7 goes into this and this. What that means is I can undistribute or factor out a 7, and when I do that, I'm going to be left with a v squared and a minus 9. Double check, 7 times v squared is 7v squared. 7 times negative 9 is negative 63. Check. Okay, so that is step 1. And these are two-step factoring. So what's step 2? Well, look at what's left. Notice that that is a difference of squares binomial. So we can factor that guy. Okay, now this 7 is just going to hang out in our final answer. What I'm going to do over here is I'm just going to focus my attention on just this part, the difference of squares binomial. Right? So I got v and I got 3 to work with, which means I got v plus 3 and I got v minus 3. And then that is not our final answer. We need to add to that or include with that a 7. So I have 7 times v plus 3, and then also all that is multiplying v minus 3. So I have the greatest common factor out in the front, and then I have these 2 linear binomials afterwards. So step 2 was factoring the difference of squares. Step 1, take out the GCF. Step 2, factor the difference of squares binomial. Okay, let's do a couple more. And this video is getting on the long side, so we'll kind of probably end it there. Okay, so let's look for a common factor. Looks like a 3. So let's go ahead and take out a 3. Okay, when I do that, I'm going to have v squared minus 5v, and then I think that's going to be 16 minus 16. Okay, so that was step 1. Now step 2 is to factor this guy. Now this is a quadratic trinomial, so my strategy here is to find factors of negative 16 that combine to be a negative 5. I'm second guessing myself on that 42. I want to make sure that that's actually 16. Otherwise this is going to throw me off. Oh, it's 14. See? Okay, cool. So 42 divided by 3, excuse me, is 14. Not 16. So this needs to be a negative 14. Whew, that changes everything, right? Okay, so factors of negative 14, they have to multiply to negative 14, but when we add them together, they have to be negative 5. So it looks like we're going to have probably a negative 7 and a positive 2. Let's double check. If I multiply these, do I get what I'm after here? Yes, I do. If I combine them, do I get what I'm after here? Yes, I do. So the quadratic binomial right here, excuse me, quadratic trinomial right here, factors to v minus 7 and v plus 2. But don't forget that I originally took out that greatest common factor, and so that is one of the factors of my final answer as well. Okay. I'm hoping for one of these. Ooh, that's a good one. I'm hoping for one of these that's a perfect square trinomial. So let's do one more. We'll do 24 here. Okay. So if you look at all those, notice that the greatest common factor is 4. Okay, so pull that guy out. That leaves us with an r squared minus 20r plus 100. Okay. Now we could factor this trinomial a couple different ways. We could use our cross method like we did up here. But you also might notice, wait, hold on a second. that is 10 squared, or negative 10 squared. And that is negative 10 times 2. Sorry, that looks like a squared. Let's make that a multiply. Okay, so we have that pattern that we saw up here. Now actually it's like very similar to this one. In fact, it has the same letters and everything. So yeah, this actually is a perfect square trinomial which factors to r minus 10 times r minus 10. Remember there was that 4 out there from the beginning when we factored out that 4. And so final answer, what we could do is we could write it like this, which is kind of neat, a little shorter. Okay, so what we saw there is the 3 different kinds of factoring that we did today with a greatest common factor, right? So pull out a greatest common factor, there's a difference of squares binomial. Cool, how do we factor a difference of squares? Conjugate pairs. Awesome. Okay, here we factor out the GCF of 3. What's left? It's a quadratic trinomial. What do we do for those? Cross method. Awesome. Finish it off. Here we factor out the 4. What was left? Well, it's a quadratic trinomial, just like we had up here, but it's a special quadratic trinomial. It's a perfect square trinomial, where this is 10 squared and this, excuse me, well, it's negative 10 squared and this is negative 10 times 2. So I'm actually going to have double negative 10s. I'm going to double negative 10 to get the middle term, and I'm going to square negative 10 to get the last term. And so we can write it like this. So any method of factoring that we've talked about, you can always throw in a greatest common factor as an extra step, pull that factor out, and then factor the rest of it the way you normally would. Okay, so keep practicing. Pull out those greatest common factors, see what you have left, and then factor using the techniques that we've talked about in class, and you should be good. Thanks for watching, guys.